Yes.
Okay, welcome everyone to this session of the seminar on PDEs and applied mathematics that we have been celebrating since 2020. Today we have the honor and pleasure to have with us Professor Emmanuel Trelat, a full professor and director of Laboratoire Jacques-Louis Lyon in the Sorbonne Université of Paris. He obtained his PhD in the University de Bourgogne in 2000 under the supervision of Bernard Bonnard. After that, he worked as an assistant professor in the University of Paris-Saclay and as professor at the Université d'Orléans. Nowadays, he's a member of the Group de Travail Control, which organizes regular, very interesting seminars in the area of control theory. He is also an associate editor of several recognized journals related to the areas of control theory, PDEs, and other fields. On the other hand, we can mention as well that he has won very relevant prizes and distinctions since 2006, such as junior member of Institut Universitaire de France, the Blaise Pascal Prize, or the Felix Klein Prize. He has been elected as a member of Academia Europaea and as a speaker in the ICM in 2018. Lastly, we will say that he has supervised many doctoral and postdoctoral students since 2007, and his research interests include control theory in finite and infinite dimensions and Riemannian geometry, among others. So thank you very much, Emmanuel, for having accepted our invitation to give this talk, and all yours.
Thank you very much for your so kind introduction. Thank you. And many, many thanks for this kind invitation. I appreciate very much. So I'm happy to present some works, still ongoing works with Thierry Paul, about various notions of limits. I mean, let me make my introduction. Imagine that you are considering finite particle systems. So there are many, many examples, and I'm going to give examples. But for the moment, please do consider your favorite particle systems with, let's say, a large number of agents. And imagine that you want to let the number of agents tend to the infinity. That is, you want to pass to the limit in some sense. So you want to pass from the microscopic model to some maybe mesoscopic or maybe even macroscopic scale. There are many existing limits in the literature, ranging over mean field limit. There is leading to the so-called Vlasov equation. There is also the Liouville equation. There is also the concept of hydrodynamic, of graph limit. So what is all of that? I'm going to draw a kind of survey on these various kinds of limits and provide you with several generalizations. And at the end of my talk, as a surprising consequence of this study and of these slight generalizations, I will show that any PDE, actually any quasi-linear PDE, can actually be obtained as the limit of finite particle systems. I will even show that it is completely constructive. So what I want first to show, I'm sorry for this big picture, but I'm going to explain it in detail. What this big picture shows is the various relationships when you want to pass to the limit in a given particle system. So the particle system, where is my mouse? Here. Oops. Oh, can you see my mouse when I move it? Yeah, thank you. Thank you for the confirmation. So you start from a given particle system, and let us say that you want to pass to the limit in various sense. So the main limit I want to consider in order to come to my surprising consequence is this continuum graph limit. So I'm going to start in particular with this limit. But before starting with the limit, let me present a particle system. So what I'm going to consider is very general. You take a particle system in the form of this differential system here, where psi I is, let's say, the ith agent. There are capital N agents that interact together according to this dynamical system as you can see, this dynamical system is a kind of average of interactions. You can think of the mapping Gij as being a kind of interaction mapping between the two agents I and J, say. But as you can see here, I'm going to consider agents that can be distinguished. So on my slides, I have written particle, but maybe the word particle is not so much appropriate, because when you think of particles, you think maybe that they are indistinguishable. But no, in my talk, and this is important, I want to be able to consider distinguishable particles, distinguishable agents. A very, very typical example that we can keep in mind, because it will be important, is the so-called Exelman and Krauss first-order consensus, or opinion propagation model, in which the interaction, as you can see, is very easy. It's a linear interaction, meaning that the evolution of the agent number I is an average of interaction over all possible agents with a coefficient of interaction modeled by the coefficient sigma ij here, which is a kind of interaction between the agent number I and the agent number j. Okay, but there are many other celebrated particle systems, like Kuckersmeil, for instance, and many other that you can know. Well, in order to prepare the passage to the limit, I'm going to do a very crucial assumption, which will also, from now on, allow the agents, or the particles, to be distinguishable. The main assumption that I will do is that there exists a continuous mapping G that, in some sense, as you can see at the bottom of my slides, that in some sense interpolates between all possible interactions. I mean, there exists, let's say, a metric space, capital omega, which stands for labels. I'm going to tag the agents with a label xi, like it is like if it was the color of the shirt, for instance. I have a black shirt, you do have a yellow shirt, and this is your label xi. You see, it's a kind of label. You distinguish agents. We are not indistinguishable. And I assume that this mapping G is interpolating, as you can see, between all interactions mappings. That is, G of xi, xj, and so on, is equal to the mapping Gij. And the fact that this mapping is continuous is also very important. It stands for the fact that when now you will make evolve capital N, you will not be allowed at the limit to switch between completely different systems. It gives a kind of compatibility assumption. For instance, before coming to examples, under this mapping, now I am allowed to rewrite the particle system that is at the top of my slides as this particle system being here, where I see, in some sense, the label xi for each agent as a kind of fixed parameter, as you can see. But now the important fact is that we have a uniform map, capital G, that models the particle system. Let me just give an example for the Exelman and Krauss opinion model. So previously I told you that the interaction coefficients are the coefficients sigma ij that are here, and my assumption requires that there does exist a kind of limit map, sigma, a kind of limit function that interpolates, as you can see, between all interaction coefficients sigma ij, which is, if you think about it, a very natural assumption. And by the way, nowadays, such a kind of map of function sigma is called a graphon in the vocabulary, in the wording of graph theory. It's exactly a graphon. Okay, so thanks to this assumption, let me show you how to very naturally pass to the limit, to the so-called graph limit, or also continuum limit. It's quite easy, and I will be quite formal about it. It is just relying on the well-known Riemann sum convergence theorem that is recalled here on my slides, that of course everybody of you knows in 1D because we learned it at school, right, in first year. But actually there is absolutely no difficulty to have multi-D versions of the Riemann sum theorem. It perfectly works. I mean, let's say that you have a space, capital omega, that is drawn here as a domain, like in PDE. And like in PDE, let us imagine that we have a kind of mesh of capital omega, that is a partition. You partition capital omega into some subdomain omega I. Each omega I, let's say, has a fixed measure, let's say 1 over n, because we want to let n tend to the infinity. Like in PDE, is like when you discretize a PDE, right? And what is a tagged partition? A tagged partition is when in each cell, omega I, you tag a point, you choose a point xi, which stands for the label, which stands for the color of the shirt, as I said before. And now the Riemann sum theorem just says that when you integrate a function f on capital omega, then for sure such an integral can be safely approximated by a sum, which is just 1 over m sum of f of xi, which is a very familiar theorem. So let us keep this theorem in mind. And now let us come back to the previous version of my particle system that is here. Okay, xi I of t is equal to 1 over n sum over j of the interactions, right? And now formally we just have to pass to the limit, and this is just passing to the limit is just allowed by the celebrated Riemann sum theorem I was recalling before. So I mean, passing to the limit just turns the 1 over m sum over j into an integral that is there. And this is the very, very simple and obvious way in which you can pass to the limit in the particle system in order to obtain what we can call at this step a continuum limit equation, which is also exactly the concept of graph limit that has emerged several years ago. So you turn the particle system at the limit when the number of agents tends to the infinity to, as you can see, to a differential equation in infinite dimension, which is of integral form. It is not difficult. It is not difficult to obtain convergence estimates. Let me just show how they can be written. In order to compare particles with the solution of the continuum limit, let me lift the particle system as a function on capital omega. In that way, if you have a solution of the particle system given by the xi I of t, well, I define on the domain capital omega, on each cell capital omega I take the constant function of x, which is equal to xi I of t. So you understand that this yn of tx that is written here is a piecewise function of x that is in each cell omega I, constant in x, equal to xi I of t, right? It is a lift of the particle system. Now that I have a lift, I can safely compare the solution of the particle system, look at here, with the solution of the limit equation. And as you can imagine, thanks to the Riemann sum theorem, under assumptions, under regularity assumptions, you immediately have the fact that yn does converge to y as n tends to the infinity with a convergence estimate that are, let's say, like 1 over n, something like that. It is not at all surprising, of course. And it is completely standard. And I do claim that this kind of result is exactly the concept that we see in many, many studies nowadays. That is the concept of graph limit, of graphen, right? That's it. This is exactly the Riemann sum theorem. Okay, it is actually the important concept in my talk, but I promised you that I would survey a bit on various limits. Another very celebrated limit, and I will show then the relationship between them, is the so-called mean field limit that leads to another equation that is the Vlasov equation. Let me recall how it goes. The Vlasov equation is, let me start directly here. The Vlasov equation is a first order equation, a kind of transport equation that is non-local. It's a non-local transport equation. Inside the divergence that you see here, you have a vector field, capital X, that depends on a measure, and that is defined as the integral against the measure mu of the interaction mapping capital G. Okay, this is the celebrated and familiar Vlasov equation. To plug, let me directly show this slide. To embed the particle system into the Vlasov equation, it is well known that you embed the particle system into an empirical measure. And the fact is that as soon as you take a solution of the particle system, then the corresponding empirical measure is exactly a solution of the Vlasov equation I showed you. So it is a way to embed properly and rigorously the particle system into the Vlasov equation. So the Vlasov equation is here. Of course, there is no difference with what is well known in the literature, except that here my measures, mu, also depend on the parameter x, that is the label, the color of the shirt, as I said previously. This is the only novelty with respect to the well-known context of Vlasov equation. So in some sense, you can think of this Vlasov equation as a kind of Vlasov equation that is parametrized by the label x. And that's all. That's the only difference. So for instance, if you want to recover the classical Dobrushin estimates, well, there is absolutely no difficulty. It works as usual, except that you just have to deal with this additional parameter x. This kind of Dobrushin estimates, for those who do not know what is a Dobrushin estimate, it's exactly a Gronval lemma, actually, that's all. It's the equivalent of Gronval lemma for usual ODEs, and that's all. So this is the Vlasov context, the mean field limit. The mean field limit is also referred in the literature as being the mesoscopic level. I will explain why in 1 minute. Before coming to that point, let me also give another very classical lift, which is the Liouville equation. So we can also embed the solutions of the particle system by Dirac embedding to the so-called Liouville equation. Let me recall how it goes. Consider again the particle system that is here, and write it as a system with a vector field, capital Y, in RD to the power n. So in a very, very big space. Okay, you write all equations of the particles and you obtain a big particle system in Rd to the power n. So you obtain a big vector field that I denote by capital Y, of which I do consider the flow that is called the particle flow, right? If you do this, then the Liouville equation is nothing but this usual local transport equation in which the transport is realized by the vector field capital Y. Okay, so it's different. It's completely different from the Vlasov equation. The Vlasov equation was living in Rd, while this transport equation is living in the big space Rd to the power n. It's a local transport equation, and the solution of this Liouville equation is, of course, the push forward of the initial condition under the particle flow. And then the embedding is different. You embed the solutions of the particle system as a pure Dirac mass that is the solution of this Liouville equation. For people dealing with probability, this Liouville equation is very familiar because it allows for probabilistic interpretations. Now, interestingly, what is the relation between Liouville and Vlasov? Because as I said, Liouville is a local transport equation in the very big space, and the Vlasov equation is also a transport equation, but non-local, in the small space Rd. Actually, there is a relation because if you know the solution of the Liouville equation, you can take marginals of it. So you can project the solution rho of t of Liouville onto the small space. And you would indeed expect maybe to recover the Vlasov equation, right? Actually, it's not exactly true, but it's also well known. It's a part of physics. If you take, for instance, the first marginal of rho, and that you have symmetrized, then it converges to the solution of the Vlasov equation as capital N tends to the infinity. So you recover the Vlasov equation whenever the number of agents tends to the infinity. And actually, this result is widely more general. When you take the kth marginal of rho of t, that is, you project onto Rd to the power k, then the fact is that you do converge to the product, the kth product of mu of t to the tensor product k. That is, at the limit, the kth marginal of rho of t becomes a tensor product. This is well known in quantum physics because this property is called propagation of chaos. So we recover it also here in the slightly more general context, depending on x, as I said. I'm sorry for that. It's just a rapid survey, and then I'm coming back to the macroscopic equation. The last fact I would like to mention before coming to my final point is that, so I showed you the relationship, let's say, between Liouville and Vlasov. It's a kind of projection by marginals. I did not yet mention the relation between the Vlasov equation, which is known as the mesoscopic level, and the continuum limit, that is the macroscopic level. Well, there is also an additional projection, and it's another part of mathematics that is called the hydrodynamic limit, that is related to another part of physics, that is thermodynamics. In the concept of hydrodynamic limit, when you are given a measure mu, let's say on capital omega times Rd, then there are usually three macroscopic quantities that you may want to consider. The first of which is the total mass of the measure, that is just the integral against psi. So here it won't be interesting because the mass is always equal to 1. We have probabilities. There is the moment of order 1, that is when you integrate mu x against psi. That is, in physics, called the speed. And this is the main quantity of interest. And there is the moment of order 2, that is in statistics the variance, right? And that in physics is called the temperature. Okay, so let us look at what these quantities mean in our general context. So let us take mu, a solution of the Vlasov equation, and let us consider the corresponding speed, that is the moment of order 1. That is, you integrate mu against psi. And let me define it as y of t and x. Then, whenever the interaction mapping G is linear with respect to psi and psi prime, as it is the case in my favorite example, the Exelman and Krauss system, then you exactly check in 2 lines that y of t is exactly a solution of the continuum limit equation. That is, you have a safe and a clean, rigorous projection of the Vlasov equation onto the continuum limit equation. And this is why we are now allowed to call the continuum limit an Euler equation, because it is really the result of a hydrodynamic limit. So this is why we can definitely call it an Euler equation. In full generality, when capital G is nonlinear, it is not exactly true that the speed is a solution of the continuum limit equation, because you have no closed equation, as it is also well known in this field, in hydrodynamic limits and quantum physics. You have actually a hierarchy, a BBGKY hierarchy of coupled moments, and the projections only work if you consider the so-called monokinetic case of pure Dirac mass. But well, and also in passing, I would like to mention a funny fact for those of you who are interested in proving consensus results. When you do consider the temperature, that is the moment of order 2, in the Exelman and Krauss model, my favorite example, you can easily show, it's also in 2 lines, that the temperature always decreases exponentially, which is also a well-known fact in thermodynamics, right? But actually, if you interpret it at the level of consensus system, this very simple and general fact gives you a very obvious proof of convergence to consensus. For me, it's still a mystery why it is so simple, actually. But I mentioned this fact in passing. But so this closes the kind of survey I wanted to draw about what are the various ways to pass to the limit in a particle system when you let the number of agents tend to the infinity. But as I told you, the most important for me and for my talk is the first one, also the most evident one in some sense, that was the graph limit. When you let me repeat, when you let capital N tend to the infinity in this 1/n times the sum, well, that's very easy. You do obtain an integral. That's it. That's my message. Now let me give a surprising consequence of this, because I'm going to show you that, surprisingly, any PDE that you know is actually a limit of a finite particle system that you can really construct. That's surprising. Let me take as an interaction mapping in my interaction systems, capital G, which is a sigma of x prime times psi prime, which is in some sense half of the Exelman and Krauss system. Okay, I'm just forgetting the minus psi, but we don't care. let us look at what kind of Euler of continuum limit we did obtain. We obtain dty equal ay with ay that is this integral, right? This is what I showed previously. This was the way that we turned a sum into an integral. Okay. So what I'm saying at that step is that passing to the limit in particle systems, we do obtain equations in infinite dimension that have the form of dty equal ay, with a being an integral operator. Are we happy? Well, not so much, because it's not a PDE. It's not a PDE because the operator that you have here, it's a non-local operator, but it's a Hilbert-Schmidt operator. It's a bounded operator. And so, question, could we, by this graph limit procedure, produce real PDEs? The answer is no, because you do obtain a bounded operator at the end. So, question, how can we generate unbounded operators? Well, look at again the form of this bounded operator that you obtain. It's an operator with a kernel, sigma. Okay, but finally, it's not so far from any possible linear unbounded operator, right? Because if you think about the Schwarz kernel theorem, it says that any linear operator acting on spaces of functions is of this form, right? With a Schwarz kernel. But the difference with respect to the top operator here with a sigma is that the kernel, A between brackets here, is not a function, of course, but a distribution, right? For instance, if you think of the operator capital A being d over dx, the Schwarz kernel of A is not a function, of course. It's minus Dirac prime. It's the derivative of a Dirac. But now the idea becomes clear. We should approximate, we should smoothen the Schwarz kernel with a new parameter epsilon in order to obtain a smooth function sigma epsilon, and thus come back to the context of a classical continuum limit equation. So this is the idea. And indeed, we can always do it. Actually, it works for quasi-linear operators, that is for almost all PDEs that you may know. So it works as follows. You do consider the Schwarz kernel of your favorite operator, like a Laplacian, for instance, or whatever. It works also for Navier-Stokes, no problem. Then you smoothen the Schwarz kernel, and you call the smoothening the function sigma epsilon here. Once you have smoothened sigma epsilon, you have obtained a bounded integral operator A epsilon. And so you have obtained the continuum limit equation that I was talking about previously. And so coming back by making exactly the converse, I do now turn an integral into a sum. So exactly the converse that I did previously. I still use the Riemann sum theorem, as you can see. I give you here an explicit construction of a particle system of which I do claim that it will give an approximation of my PDE, of my initial PDE. But now you see the difference. The difference is that I do have two parameters now. Not only I have the number of agents, capital N, but I have also the second parameter, epsilon, that is used in order to smoothen the Schwarz kernel. I have two parameters, not only one. Thanks, actually, this is the application to any quasi-linear PDE that you may know, okay, but I can go quickly. By applying the general estimates I was showing you very, very rapidly before, what I now claim is that indeed, thanks to this particle system approximation procedure, I do obtain a completely general approximation between the particle solution and the solution of the PDE, the solution of the Euler equation, say, that is always like the discrepancy, as you can see, is always the sum of two terms. A term that is like epsilon, and a term that is horrible, that is like 1 over n times an exponential of 1 over epsilon, and a horrible term. It is not surprising in this discrepancy that if for n being fixed, I let epsilon tend to 0, then I have a blow up, of course. So it gives nothing interesting. It's not a surprise. And instead, if I fix epsilon, well, I recover a discrepancy like 1 over n, but which is also not interesting because for epsilon fixed, I don't have my PDE. I want to let epsilon tend to 0. So what you see here is that you have to let epsilon tend to 0 and capital N tend to the infinity together at some scale. And if you optimize the sum of the two, well, what you do obtain is that you should let epsilon tend to 0 like 1 over log n. This is the best compromise. And then the final estimate in that case that we obtain is that the discrepancy, and this is my final result, the discrepancy between the solution of the PDE and the particle system I showed you is like 1 over log n. And what I claim, and this is my main message, is that it is a universal approximation. It's universal. I mean, I made almost no assumption. It's surprising, right? It's very surprising because we are used to have particle approximations for PDEs under maybe very strong physical assumptions. That's true. But what is true too, if you review the existing literature, is that in the literature, what we do obtain when it works is approximations that are much better than 1 over log n. Usually we do expect something like 1 over capital N, right? Like in finite element methods or whatever, okay? So okay, this approximation that I show you here is universal. It's done without any physical approximation. But if you think about it, 1 over log n is kind of unuseful because it's a bad approximation. It is too much general. If you think about statistical physics, what is a domain in statistical physics? A domain is, let's say, capital omega of volume 1. In statistical physics, say, PDEs do not exist, right? You only have particles. How many particles do you have in a volume equal to 1? Well, let us come back to the basics. You have, let's say, 10 to the power 23 particles, which is the Avogadro number, right? Okay, so in that case, what is the discrepancy that we have obtained? 1 over log n. Yeah, but look at log n is equal to about 50, so it's very bad. 1 over 50, it's very bad. Any numeration people would laugh about such an estimate, right? And they are fully right, of course. So in some sense, this remark, I think, explains a bit the paradox that you have that I did not make any assumption while deriving this system. It is not moral. So my conclusion is that I see, in some sense, this discrepancy 1 over log n as a kind of physical barrier. I mean, any mistake, any error, any discrepancy that is better than 1 over log n, like 1 over n, is physically relevant, certainly. But any discrepancy that is 1 over log n or even 1 over log n is certainly not physically relevant. It's certainly mathematically interesting, but maybe physically not so much. So this is my conclusion. I'm still I still find a bit mysterious, actually, this kind of universal approximation procedure that I showed you. I'm still not completely sure of what this implies, right? What I'm rather sure of is that, so as I said, I did not make or almost no assumption on the PDE. So every PDE can be approximated by a particle system, but with a discrepancy that is very bad, with an error that is very bad. My claim is that as soon as you plug some physical context into the PDE, as soon as it is a physical PDE, like Navier-Stokes, like Euler, like something like that, something in which you do know an energy, something decreasing, then you can much improve, as you can expect, the previous estimate. And maybe you can hope to have an error like 1 over capital N or something like that. So would this procedure I showed you have consequences in numerical analysis? I do not think so. But I see maybe a possible application of it. It is, for instance, in mathematical biology, in many situations, you know some PDE models, but you do not know any finite dimensional models like particle models. So maybe this kind of procedure can give you a kind of recipe in order to derive from a given PDE that you have a particle system that might maybe be useful in some studies. And also another thing that I would like to investigate in the future about this study is add some controls to those equations. I mean, I would like to be able to control the particle system and also the limit PDEs that I do consider, and try to obtain a compatibility between the limits at the level of the controls. Thank you very much for your attention.
Okay, thank you, Emmanuel. Thank you very much. It was for me an amazing talk. Yes, many interesting things. And we will give now the opportunity to the audience if they want to ask something or make a comment. So you are free to you can write in the chat or open the micro. Juan has allowed you to talk. So
Emmanuel, thank you very much for your nice talk. I am like, so it's a point that I think I missed. You have this measure mu that solves the Blasov equation, no? And then you pass to the limit and you obtain the Euler equation. And you have a different measure in the Euler equation. Is there a recipe to find this measure? Because you have like different measures in all your equations, not in the particle system, but in the others, that I don't know which is the relation between the measures.
Oh, yeah, I'm sorry for that, Luz, because I had to be very quick, unfortunately. So your question is in between Vlasov and Euler, right?
Or in general, because you are moving from one measure to another one. So how do you find this other measure, or I don't know.
Oh, yes. So what I have tried to draw is precisely, so for instance here, because I insisted a bit more maybe in my talk, was the relationship between the Liouville equation and the Vlasov equation. So my claim here, for instance, is that if you take rho, a solution of the Liouville equation, and if you take marginals of it, that is, you do project rho on the first copy of the tensor space. The tensor space is Rd to the power n, because it's the number of particles. But if you do project rho, which is a measure on the big space, onto the single space RD, then my claim is that at the limit, when capital N tends to the infinity, you do recover a measure that I denote by mu that is exactly a solution of the Vlasov equation. So essentially, you pass from Liouville to Vlasov by projecting measures, right? And for instance, you pass from Vlasov to Euler or to continuum limit by taking a moment. That is something a bit different. It's also a kind of projection, right? But it's anyway something a bit different because here you take mu, a solution of Vlasov, right? And you integrate mu against the variable xi. That is, you take the first moment of this measure. And you keep x as a parameter, so that what you recover is a function of t and x, right? And the claim is that, at least in the linear case, for the Exelman and Krauss case, you can check that if mu is a solution of the Vlasov equation, then y is a solution of the Euler equation. So essentially, these are projections.
Okay, thank you very much, Emmanuel.
You're welcome, Luz. You're welcome.
Thank you. Is there any other question? I would like to say, Emmanuel, that it was amazing when you said that this key or very big discovery, at least for me, that any PDE is a limit of a finite particle system that we can construct.
Yes.
For
Yeah,
me,
it's
it was
surprising.
incredible. It's crazy because not
Yeah.
because its own relevance in this context, also because I think that it could have a lot of influence in future results of PDEs. No, I think.
I don't know. Maybe thank you for your very kind remark.
Yes,
I do not know. It's still a bit mysterious for me, I must say, because there are already some PDEs for which we are not surprised that there are some particle approximations. Celebrate examples are fluid equations like Euler or Navier-Stokes equation, because it is known since the Second War by von Neumann, and it has generated the Monte Carlo methods and then the particle methods for fluid equations. So it's already known in this context. But for instance, it's not known for many other equations, such as, for instance, for the Schrödinger equation.
Yes,
it's crazy. I mean,
yes.
But the fact is that for the Schrödinger equation, you can derive a particle approximation.
Incredible.
You can also derive a particle approximation for the usual heat equation. And believe me, it's completely different from the usual Brownian motion that is known as an approximation of the heat equation. It's completely different. And also, if you implement this procedure on a usual transport equation, then you do obtain something which is also completely different from the usual characteristics.
Yeah.
It's something else.
Yeah.
And I do not know. It's still a mystery for me.
Yes.
But be careful, because as I said, it is a universal approximation, but the price to pay for this universality is the very, very bad decay rate. The decay rate is 1/log n. It's horrible. It's a very, very bad decay rate.
Yes.
This is the price. This is the price to pay.
Yes. Thank you. Thank you very much for your talk, Emmanuel. Sincerely. I think that we have to stop because now there is another speaker. So I'm sorry, Emmanuel, but we have to continue.
Sure.
Thank you.
Thank you very much, Professor Trelat, for your excellent talk, and see you other opportunity.